Hi, and welcome back to Applied Machine Learning. In this lecture, we're looking at supervised learning. And in the previous video, we saw what supervised learning is, and we looked at the structure of a supervised learning problem, and then we focused more deeply on a supervised learning dataset and its structure. In this lecture, we are going to continue our discussion of the anatomy of the supervised learning problem, and we are going to now focus on the algorithm itself. So, as we mentioned earlier, when we want to apply supervised learning to a new task, we have to provide the computer with a data set and a learning algorithm that when the computer will follow the instruction of the learning algorithm on this combined with this data set, it will understand the structure of the data and learn a predictive model which we can then use to make prediction and solve other kinds of tasks. In the previous video, we looked at what is a data set and how we can define it and make it more precise using mathematical notation. Let's now look at what an algorithm is, and let's define components of an algorithm more formally. Similarly to how data sets and how supervised learning itself has different components, we can also think of a set of three components as comprising a supervised machine learning algorithm. Those three components are, first of all, a model class, then there's an objective and an optimizer. You can think of the model class as the set of all the possible models that we could infer from the data. These are all the different ways in which we can map inputs to outputs, and we will a typical learning algorithm does not consider the set of all possible mappings, but it restricts them to a particular set that have a particular form, such as the linear models that we saw earlier. Then, given a data set, we want to be able to represent our knowledge about some models being better than others. Intuitively, if a particular model within our model class fits the data set well, then it's a good model. And in order to define what it means to fit the data set well, we use here an objective function, which defines the extent to which a model is a good fit for a particular data set. And finally, given this objective function over the set of models, we need to find a model which maximizes this objective, or which optimizes this objective, which is a good model. And an optimizer is a component that will search for the best predictive model in our class according to this objective function. So these are three components of a supervised machine learning algorithm, and to make this a little bit more precise and a little bit concrete, let's dive deeper into each one of these components. But before we go further, let's again look at an example from our diabetes data set. So here we have we're going to load again this data set as we did earlier, and here I am printing the main data frame that contains the input features of this data set. We will use this as a running example in our data set in this video. So first of all, let's start with the question of what is a model. And for the purposes of this course, a machine learning model, or at least a supervised learning model, is going to be a function which will map inputs to targets. So it's some function that maps from the input space to the target space. We will later see more general types of models, which, for example, can output probabilities, but at least for the sake of this lecture, we will start with the following definition. Now, as we saw earlier, often models are defined by a set of parameters, like the linear models that we saw earlier, which were lines that had a slope and an intercept term. And we will denote these models with this particular form in which there is a superscript theta, which is the set of parameters that parameterizes this model. And now for each different value of this subscript theta, we have a different mapping between the target space and the input space. now that we know what a model looks like, or how we can define a model using mathematical notation, we can now define a model class using mathematical notation. In its most general form, a model class can be any subset of the set of all possible mappings between features and targets. In practice, in order to define this set of models, we often use parameters. So as we saw earlier with linear models, we can define, for instance, the set of linear models as the set of functions that have a linear form with these linear parameters, where these parameters live in a specified set, which is, for instance, the set of all valid linear models. These are bits of notation. Let's now look at let's look at a more specific example of what this might look like. Let's again revisit our example of linear models here. So we saw a simple linear model earlier, which was a line that would map the BMI into diabetes risk. This was a model that took a one-dimensional input and produced the diabetes risk as the output, and the relationship was just a line in one dimension. We can generalize this approach to linear models of many variables which have this particular form. Here, our input x has d different dimensions, has d features, and our model assumes that the output target y, such as the diabetes risk, is a linear combination of the input features, which are each weighted by a term theta, which assigns a particular which assigns a quantitative measure of the importance of this term. So this is a class of linear models over multiple variables. Let's now look at how we can apply such a model. Here I am going to again load the diabetes data set, and I will take I'll take 20 points from this data set, and then I will again fit our linear scikit-learn model to this data set to output a set of predictions. Again, I am using this linear regression model here as a black box, and in the next lecture we will see how the internals of this algorithm are implemented. But just to give you an example of what a linear model could look like, here I have just invoked this algorithm to obtain predictions for the same set of 20 points that we had, plus the same 3 new data points that we used in our earlier example. And here, because this is a linear model of many variables, you can see that actually our predictions for these points, which are the x's, are actually closer than they used to be with our linear model example, with our one-dimensional linear model, which shows that adding extra features here is actually helpful. So we have defined what a model class is. Let's now define what an objective is. An objective function, which is also called a loss function, in many applications this term is also used. You can think of it as a function which maps, which assigns a score to each model in our model class. And this score can be, we can think of it as being a positive number between 0 to infinity. And this describes the extent to which f fits the data in our data set. So if a model fits the data well, it will have a low score. Or we can think of it as saying that it has a small loss. If the model is a bad fit and it fits the data poorly, then its loss, or the value of this objective function, will typically be high, and it will be perhaps closer to the infinity part of this range. Again, if the function f is parameterized by theta, then we can simply make the objective j be a function of the parameters themselves, and now we can just formulate it as mapping parameters to this to the output range. If the model is parameterized, then these two notations are going to be equivalent. They operate over the same set of possible functions. So let us look at some examples to make this precise. Let's say that we had a particular model, which I'm denoting here as, again, f sub theta. And f sub theta outputs a prediction for every input x. And we have access to a training data set of examples, x and y. So how would we define what it means for a model for some value of theta to have a good fit over this data set? And how would we say that a model has a bad fit? Well, one approach, which is often used in practice, is to use this term called the mean squared error. The mean squared error is simply, as the name implies, the average squared error between what the model predicts and the true label. So intuitively, we say that a model has a good fit, or it has a small mean squared error, or it has a small value of this objective or loss function if the values predicted by our model for some value of theta are close to the true values, to the true labels, to the true targets that are given to us in our training data set. And conversely, if our model outputs targets which are really far from the ones that are set here to be the true targets, then we will have a high loss or a high value of this objective function, and this will be a bad fit. Intuitively, we want the model to output, we want to say that a model is good if its predictions match the true targets which are available for this training set. And this is the intuition that this function provides us. Now, of course, the mean squared error is not the only way of measuring fit, and there are many such functions, and we will see quite a few of them in this course. But just one example of a different function that could be used is the absolute error, or sometimes called the L1 error. This is just the average of the absolute value difference between what the model predicts and the true label that we expect to be predicted for this particular input. We can try out some implementations of these two loss functions. Here I have just imported them from scikit-learn. They are available as part of scikit-learn in the metrics package, but of course it will be very easy. It will be just one line of NumPy to implement them manually. Here I have two sets of points, y1 and y2, and I can compute both the mean squared error and the mean absolute error of these points using these functions. And we can see here that these are the values that hold for these data points. So we have now seen what is a model, what is the model class, and what is an objective function or loss function. The remaining missing piece is the optimizer. So we need some way of finding a function, finding a model which has a good fit, which optimizes our objective function. So essentially, an optimizer is an algorithm that will solve the following problem. It will find the function f in our model class, which minimizes our objective value. And of course, this objective value is defined for a particular training set. This function will have the best fit on the data. And again, if the function f is parameterizable by theta, the optimizer will minimize j of theta over the set of all valid parameters. Now, there are many ways in which this process can be performed. We will see a few practical ways of optimizing models starting in the next lecture. But just to give you an example that we have seen before, when we were invoking the linear regression algorithm within the scikit-learn.linear models library, this algorithm was implicitly using an optimization procedure to solve the following optimization problem. So here is an example of an optimizer, and then there is a particular approach to optimizing this problem that is implemented in linear regression. In fact, there are multiple approaches. One of them is called is performing something which is called gradient descent, which we will see in the next lecture. And another approach would be to find the minimum by solving what is called a set of normal equations. We will also see that in the next lecture. But essentially, for now, I just want to mention that there are algorithms from the field of optimization which are designed to solve optimization problems like this one, and and the optimizer of a learning algorithm would implement such an approach to find the theta that provides the best fit to the data. So here, just to give you a small demo, I am running this. I'm again importing the mean squared error from the library, and earlier we have pre-computed in our previous video. We have pre-computed values. We have made predictions on the diabetes data set. Here we have a set of training predictions on this data set. We have the true labels for this data set, and similarly we have those 3 new data points that we have just seen. Those are on which the algorithm was not trained. This is the set of labels for these 3 points, and these are predictions we have made for these 3 points. And we can see here the mean squared error for these 2 sets of points. And finally, if we were to just generate a random set of examples, a random set of numbers, and we were to look at their mean squared error, and we would look at their mean squared error relative to the true labels for these 3 data points, we see that this number is much higher than the value of our correct prediction, which shows that indeed the optimizer is finding a set of predictions which minimize the mean squared error. Now, this is of course not showing any of the internals of these algorithms. It is just providing the intuition and the definition of all of these components. And in the next lecture, we are going to look at all of these components in more detail. For now, I just want to leave you with this overview of the components of a supervised machine learning problem. These are all components that we have seen in this lecture. And again, if I were to summarize things from the beginning, in order to apply supervised learning problem to a particular task, we need to create a data set, and we need to define a learning algorithm through which the computer will find a good predictive model that performs well both on this data set and on new data. And the data set is a combination of training examples, which contains an input X and a target Y, and an algorithm is the algorithm internally contains 3 components, which is a model class, which is the valid set of models from which we'll find the predictive model, an objective, which scores the models within this class, and finally an optimizer, which finds the best scoring model within the class according to the objective. This is a general definition into which we can place any supervised learning algorithm, and in the next lecture we are going to define very specifically some real-world, some important algorithms which are widely used and that fall within this framework, and we're going to define them by describing what each of these components look like.